Hello everyone, Brian here. So today we're going to be covering big idea 4, which is kinetics, and we're going to be going over describing rates and collision theory, so your theory behind rate laws and how do you find rates. Then finally we're going to finish off with all the graphs and different properties given certain rate laws. That being said, let's get right to it. So what is a rate? A rate is going to be the rate, so the speed at which a reaction is going to proceed in a certain direction. Rates are given in molars per second, and this unit will always be the case. So say a rate law was given for this previously, not that we found it, but that it was given to us, and the rate law took the following form. Ka and B. So first thing that we notice, both A and B were involved in this specific rate. Then there is this K value here. K is known as Arhenius Constant, and this constant has to deal with reaction kinetics. So different ways and properties and different things that affect how a reaction is going to proceed at a certain speed. And we define speed by a change in your concentration of any given reactant, or in terms of rates of appearance, the product, with regards to time. Most of the time measured in seconds. Can be minutes and hours, but most of the time does tend to be molar per second. So how do you look at this, and what else is there to do based off of that? First thing you can be asked is, what are the units for K? The units for K are always going to vary. So it has variable units. Its units need to be whatever it has to be in order to make sure that rate is going to be molar per second. If we take in this given equation, we know rate is going to be molar per second, which equals K. I don't know my units for K at the moment. Concentration of A, concentration is always in molar. Concentration of B, again, always in molar. How can you take this information and use it to find out the units for K? Let's divide each side by m squared. What ends up happening? These cancel out, and we have K equals 1 over molar seconds. In this case, this is a unit for K. We were given a different equation, say rate equals K concentration of A cubed. In this case, again, rate is going to be molar per second, which equals K times concentration of A, concentration is always measured in molar, cubed. So we're going to multiply everything by 1 over m cubed, and you end up with the units for K is going to be 1 over molar squared seconds. Collision theory. So as far as the actual theory goes in this section, this is pretty much all you're going to be seeing. The rest is mathematics and different techniques applied to finding rate laws. Collision theory has two parts. The first part of collision theory says you need an adequate amount of energy. And the second part of collision theory says you need proper orientation. This term on the first part, adequate energy, if you remember correctly, that phrase literally describes activation energy. So the first half of collision theory says that whenever you are making a reaction, you need an adequate amount of energy for this reaction to proceed. That adequate level of energy is defined as your activation energy. If we were to have a Maxwell-Boltzmann diagram for a given sample, it would look like this. Let's say this is some whatever molecule at 50 degrees Celsius. Well, it just so happens we can depict activation energy here as a vertical line going straight down. Every molecule that is to the right side of that line and under the bell curve is going to have enough energy to react. So it met your activation energy, or surpassed the activation energy. Now, another thing you can do to this is, let's say we added a catalyst. We know catalysts work by reducing activation energy. So the addition of a catalyst would shift this to the left, and now my activation energy line may look as follows. So this would be activation energy with a catalyst. And obviously more molecules in that case are going to have the prerequisite energy to react. However, that does not guarantee they will react. That only tells you that they have enough energy. In order to actually react, we need energy and orientation. But what does orientation say? The decomposition of NO2F. And it will decompose as follows. So NO2F, 2 NO2F is going to break down to make 1 NO2, 2 NO2s, and diatomic fluorine. How does this happen? If you were to draw the actual molecule itself, imagine I have nitrogen here, and then oxygens, and fluorine. And the same thing on this side. Oxygens and fluorine. Say these guys had enough energy to actually react. When they hit each other, does it make sense for somehow this fluorine and this fluorine to actually be bound and stuck together? No, of course not. They're on opposite sides of each other. So this results in no reaction because I did not have proper orientation. On the other hand, if there was another of these molecules structured as follows, so the F sides are right next to each other. Remember, we're trying to make F2 come out. When you remove the fluorine, you get NO2 from NO2F, right? In this case, given enough energy, if these two guys hit each other, you are going to have a reaction that creates 2 NO2s, and then those fluorines will be bound to each other to make diatomic fluorine. Moving on. How do you actually find rates then? There are 3 ways to find rates. You can use the chart, which there's no official name for that. We'll see exactly what I mean by a chart in a second. We can use reaction mechanisms, and then we can use the graphs. Given certain graphs, depending on the way they look, you'll immediately be able to know what rate law is going to govern them. And rate laws are just laws that govern different rates given different orders. How do you find the order of a certain rate? Say we have rate equals Ka. This is going to be first order because the sum of all the exponents attached to that concentration are going to be 1. Imagine if you had rate equals Ka cubed times B. This would be a 4th order reaction. Here we are only going to be dealing with, in terms of graphing at least, 1st order reactions, 2nd order reactions, and 0 order reactions. You will not be asked to graph 3rd, 4th, etc., etc. On top of that, 2nd order reactions can either come from Ka squared or Kab. You will not be graphing this. You will only be graphing Ka squared. However, you can be asked to find the units for K for this reaction, or a question that just so happens where this is a rate law, but as far as graphing goes, you won't be asked that. Now, if I give you the following equation, say A plus B plus 2C gives you D. Can you find the rate law? Immediately, one would be inclined to say K, concentration of A, concentration of B, and concentration of C squared. But this is wrong. You absolutely cannot do that. Given this information, the question I just asked is impossible to solve. Why? I did not give you a chart. I did not give you reaction mechanisms, and I did not give you a graph. There's a couple of other clever ways of finding them out, but these are the three main ways. The point is, if someone tells you that A plus B gives you C, and the rate because of that is going to involve both reactants, that is absolutely not true. Given only a reaction, you cannot find the rate law. That being said, let's get on to actually finding rate laws. First, you have tables and rates. So here the question says, in a study of the kinetics of the reaction represented above, the following data was obtained, blah, blah, blah. You have a certain experiments, bunch of concentrations for different molecules. On the left-hand side, my reactants, right-hand side, my products, and here rates of disappearance of BrO3. So let's see exactly what's happening here. How do you use this information to find the rate law? We know the rate law is going to take the following form. Then concentrations here, but we don't exactly know which ones. So how could we find out? We always have to pick two experiments. Let's pick two experiments and treat it as a completely normal, like science 5th grade experiment. You only want one variable and one output, one result of that variable. If we were to look at experiments 1 and 2, you see that here there is no change in my concentration of BrO3. Here there is no change in my concentration of hydrogen ion, but here there's a change. This has a magnitude of times 2. And over here is a certain change. Again, magnitude times 2. So let's call this, to make things simpler, A, B, and C. If we look at my input, my concentration of A doubled. And what happened to your output? My rate of disappearance of BrO3 went from 2.5 to 5. So it also doubled. The way you have to compare these things are always in terms of factor. Did it double? Did it reduce by half, times 3, times 4, times 1.5? Just multiples for each value. Because my input doubled and my output doubled, this is going to be a linear relation. So a first order relation. A is going to have a dependency to the first power. On to the next one. We need to locate, again, two experiments where there are as few changes as possible. If we work with 1 and 3 this time, A is constant, B changes by 1.5 times 1.5, and then C is constant. Awesome. What happens to my output? It experiences some change. Let's see what that change is. So my input, I had one change of 1.5, and my output to go from 2.5 to 3.75, and again, both are 10 to the negative fourth, we have to change by 1.5 as well. So same exact thing happens. This is also linear. It will be B to the first power. But what about the last one? Let's try to pick two experiments. Again, we always want to pick those that change as little as possible. In this case, I'm going to use experiments 3 and 4. Here, there is no change. Here, there is a change of times 2, and here there is also a change of times 2. My output might not be able to tell so easily what happens there. So let's pause and let's take a second. My input, nothing happened here, times 2 and times 2. So I had 2 times 2 to produce some output. How can we get from 3.75 times 10 to the negative fourth to 3 times 10 to the negative third? If you put that into your calculator, it ends up being that to get to from 3.75 times 10 to the negative fourth to 3 is going to be a times 8 multiple. What do you do with this information? We know this one corresponds to B, and over here this corresponds to C. But I have two inputs, so how do I know what's going to happen in my output? Well, lucky for us, we already know the dependency of B. We know it is going to be to the first power. So if I divide by 2, that gets rid of this entirely, and I can divide by 2 to the first here, which is again just the same thing as dividing by 2. If this was second order, I would divide by 2 squared, and we end up reducing this into 2, and your output is now 4. This kind of dependency is quadratic. And why is that the case? Because 2 squared is equal to 4. That means C is going to have its dependency to the second power. And now we have solved all the values for the rate law, and we have an appropriate rate law. Moving on, what are reaction mechanisms? Reaction mechanisms are a series of steps that describe an overall reaction. We may be given the following series of steps. So A plus B is going to be in equilibrium with X. X plus A will make D, and then D plus C will make B plus E. Then there may be words alongside here describing the speed. We'll get to what that means in a second. So for starters, we can take this information, add all the reactants up, and cancel everything out. We see that here, X will cancel with X, B will cancel with B, D will cancel with D, and we can simplify the reaction to be 2A plus C gives you E. But we know it is incorrect to say that the rate law is going to be Ka squared times C. It doesn't make any sense. It's not how we actually solve it. So how do we use reaction mechanisms in order to figure out the rate law? That's where these words come in. When you use reaction mechanisms, the rate law is going to be determined by the rate determining step. And the rate determining step is always going to be the slow step. So my rate becomes K times A times X. But there's an issue. X is not part of this original reaction. So how does that make any sense? Well, as it turns out in this case, X is in equilibrium with A plus B. So X can be substituted for A times B. In that case, you end up with Ka squared times B. And now we have the proper rate law for this given reaction. Two things to note for reaction mechanisms. You will always have, well, not always, but you can have catalysts present, and you can have reaction intermediates. What is a catalyst? Again, we know catalysts are things that take part of the reaction and they reduce your activation energy. How do you identify catalysts? Catalysts will always be present at the very beginning of your reaction and at the very end of your reaction. So in this case, my catalyst is B. How do you know when a reaction intermediate is going to exist? Reaction intermediates are those that get created somewhere along the way in the reaction and they get used up somewhere along the way in the whole reaction mechanism. So my reaction intermediate is X. You may or may not have them present, but if you're asked to identify it, this is what you have to do. Moving on. Let's go on to actually graphing these things. So, what is a zero order reaction? A zero order reaction is the one characterized by the following, where your rate is just going to be equal to K. Here, if we were to graph rate on the y-axis and time on the x, we end up with a horizontal line. That horizontal line is just going to be K. Not much more to be said for zero order, so let's move on from that. The one that's going to have the most questions by far is going to be the first order graph. The first order graph is given when the following occurs. My rate is going to depend on the concentration of A. If we try to graph this, let's say we're graphing the rate of disappearance of A, you will see something resembling the following. You'll get a graph that slopes down. It's asymptotic about some point, or it may reach zero. Depends on the question. Here you have time, and here you have your rate of disappearance of my concentration of A, which is always molar per second, right? More important than that, we have something referred to as the integrated rate laws. What is an integrated rate law? An integrated rate law is taking this and finding a way to normalize the function. Normalizing in the sense that we're going to take this graph and see what we can do in order to make it into a straight line. If you graph time on the x-axis against the ln, so natural logarithm of your concentration at any given point in time, you end up with the following. Now we have a straight line that came from the same data set that governs this graph. In this case, my slope of this line is going to equal negative k. And the integrated rate law is written as follows. The ln of your concentration at any given point in time is going to equal negative kt plus ln of the concentration of A. At this point in time, my concentration of A naught, is always your initial concentration. And it will look as follows. So if you have any graph, any set of data, you graph it using ln, natural logarithm on the y-axis, and you end up with a straight line that has a negative slope. That proves that your reaction is a first order reaction. What else happens in these kinds of questions? You get half-lives. A half-life is the amount of time it takes for you to lose half of your concentration. Imagine I have the following graph. What can we see here? Time, and again here, my rate of disappearance of a certain concentration. Normal graph would look as follows. But what's so important about this idea of having a half-life? For starters, a half-life is only going to be present in a first order reaction. So if you can prove that, then if you can prove that this has a half-life, or the same principles that govern a half-life, you prove that this is a first order reaction. If at this point in time, I'm going to call this 1, my concentration is 10, then at my time 2, I'm going to say that my concentration is 8. What did I do? I went from 10 to 8. To do that, you would have to take 10 and multiply by 0.8, or 80%. And this took 1 minute. If I go to my next minute, I can take this original concentration, go to that time frame, and as it turns out, the value that corresponds to that concentration is going to be 8, so my previous value, times again 80%, which gives you 6.4. So what is the general idea that governs having a half-life in the first place? It tells you that for any change in my given time, a constant value in my change is going to correspond to a constant percent drop in my y value. In this case, 1 minute corresponds to a 20% drop. Or I have 80% of the current amount remaining. And this will be the true for every minute you look in between this graph. If I went from 2.5 to 3.5, that's going to drop by 20%. If I went from 7 to 8, that is going to drop by 20%. The half-life is just the case of this, where my drop is 50%. Now, what else can happen with half-lives? We have this one really neat property. So in order to find a half-life, the easiest way by far is to take the ln of 2 and divide it by k. We can prove this, but in this video lecture, we're not going to bother with that. There's no point. Moving on, what is a second order reaction? A second order reaction is the one governed by the following equation where your rate is going to be equal to k(a) squared. You won't be graphing, again, anything that has rate equals K concentration A times concentration of B, only in this case. Again, the normal graph will look as follows. Say the rate of disappearance of A, but the normalized version looks a little bit different, or the integrated rate law. In this case, in order to normalize this function, when we're graphing against time, we graph against 1 over my concentration at any point in time. So the inverse. And your graph will look as follows. So now it is a straight line with a positive slope, where the slope is equal to K. If you take a given data set that produces this graph it against the inverse of the concentration, and you get a straight line with a positive slope, you have a second order rate law. Integrated law is then as follows. 1 over the concentration of AT is going to equal KT plus 1 over my concentration of A sub 0, where this value right here is A sub 0 or A naught. That's pretty much all for rates, guys. Thank you for your time. Trying to make these videos a little bit shorter so we can actually finish up and have everything done before your AP exam, which is Thursday now. Best of luck with everyone with your studying, and take care. On to the next one.